Welcome everyone. For today's prep, we're going to introduce the precise definition of the derivative. And with this, we're going to see how to actually construct the tangent line. And one of our key things here is this is going to require limits. So we're going to start with our construction of the tangent line. All right, so first step is if we have a curve and we want to construct our tangent line, first step is figure out the point of tangency. So we're going to call this point P. And this point stays fixed. So we're going to look at this little graphical example here. So we have our curve. And this is, some function y equals f of x. And that's what we have here. So we have this curve that we're interested in studying. And in particular, we have this one point in mind that we're really interested in. So we have our point P here, and this is going to be our fixed point. So this is where we want to draw our tangent line. All right, so how are we going to do this? Well, once we identify that point P, the next step is we're going to choose a second point. So when we try to figure out a line, we generally need 2 points. 2 points is what is required to define a line. So we're going to choose a second point, and we're going to call this point Q. And it's going to be relatively close to P, but just somewhere else along the curve. So that's what we have here. We're picking a second point Q on our curve. And once we have that second point, now we can draw a line connecting those 2 points. And that's going to be what we call our secant line. So this will be our secant line connecting points P and Q. And the goal for this is to produce our tangent line. So that's what we have here. The goal is to get this tangent line at point P. So how are we going to get that? Well, so far we only have the secant line. And the idea is we're going to keep point P, that one's going to stay fixed, but what we're going to do is we're going to slide point Q so that it gets closer and closer to point P along the curve. So we're going to slide point Q so that it gets closer and closer. And what happens is this secant line then essentially becomes, once we reach the logical conclusion there, essentially it becomes our tangent line. So let's see a little animation for how this process kind of looks. All right, so we've got our graph here, and you can see there's point P and point Q, and we choose point Q just to be kind of close to P, but in this case it's slightly to the right. And what we're going to do is, we're going to move, get that out of the way. We're going to move point Q, and we're going to slide it along the curve so that it gets closer and closer to P. And you can see, as that happens, the secant line becomes our tangent line once we reach that logical conclusion. So in this animation, or in the graph that we looked at, I chose point Q to be slightly to the right of P, but it also works if we choose Q to be on the other side. So we know with limits we can kind of approach from either side. So if we come from the left-hand side, again, we're going to move point Q, we're going to slide it along the curve so that it gets closer and closer to P. And then once we reach its logical conclusion, it becomes our tangent line. So you can do it from either side. You can approach from the left and bang, or you can approach from the other side. And there we go. So the secant line, as we move that point Q closer and closer to point P, we get our tangent line. All right, so let's go back to our notes here. And this is what ultimately leads us to our limit definition of the derivative. So when we talk about the derivative, we want to remember, we call it the derivative of the function f of x, f prime. And what this does, we've seen it before, the derivative is the slope formula. So it gives us the slope of the tangent line. So it gives us the slope of our function at x. All right, so we have this limit definition of derivative. And this is telling us how we can actually calculate from this construction our derivative, how we can figure out the slope of our curve. And it really comes from this idea of drawing a secant line and then sliding that point Q closer and closer to point P. So first, let's look at this fraction. F of x plus h minus f of x all over h. So this, kind of a mouthful, sometimes call this a difference quotient. What we're going to see, and we'll kind of go through the process, this is actually the slope of the secant line. Where we connect points P and Q. So that's giving us the slope of the secant line. And this limit that we have in front, limit as h goes to 0, that's what kind of achieves the sliding point Q along the curve. So this is what gives us our motion. So this is what moves point Q along the curve towards that fixed point P. All right, so kind of we have all the pieces here. So we've looked at how to find the slope of just a regular line connecting 2 points. And we've looked at limits now. And remember, we want to think of limits as kind of giving us ways to talk about motion, moving things around the curve. And so that's what this limit as h goes to 0 does, is effectively it's going to move, it's going to slide point Q along that curve, and we're going to move that second point closer and closer to P. All right, so let's actually see where this fraction comes from, though. So when we pick a point Q, and I'm going to move over here. When we pick a point, or if we start with our point P, we're going to give that just kind of, we'll just give that x, we'll just say it has x coordinate x. So when that's the case, point P has coordinates x, and since point P is on our curve, the way you figure out the y coordinate for a point on the curve is you just take the x value and you plug it into the function. So in this case, the y coordinate would just be f of x. So that would be our coordinates for point P. Now, point Q is we're picking something that's close to P, but just a little bit bigger or a little bit smaller, however we want to do it. And so let's say that point Q has the x coordinate x plus h. So we're close to point P, but we're adding a little bit extra. And so that's the way you kind of want to think of this h value that you see. H is just a small number. So we have our point P here, and our x coordinate for point P, and then we want to choose a second point, point Q on our curve, so we're going to go close to P, but then we're going to add a little bit extra. So what are the coordinates for point Q then? Well, the x coordinate is going to be x plus h, and again, if this is our x coordinate, the way you find the y coordinate, since point Q is going to sit on our curve as well, we just plug that into the function. So we get f of x plus h. All right, so we have these 2 points, and now we want to figure out the slope of the line connecting those 2 points. So let's look at the slope of our secant. And if we remember back, kind of one of the first things we did, slope of a line is change in y over change in x. And so we can take our y coordinate from both of these points. So let's start with our y coordinate from point Q. and subtract off the y-coordinate from point P. So we're taking our y-coordinate here, which is from point Q, which is f of x plus h, and we're subtracting off the y-coordinate from point P, which is f of x, and then we do the same thing in the denominator, but this time for the x-coordinates. So we take the x-coordinate from Q first, so we get x plus h, and then we subtract off the x-coordinate from point P. So again, this is just regular slope formula stuff. And the only thing we can do extra is this denominator simplifies. So if we simplify that down, the x here is going to cancel with the minus x, and that's what leaves us with just the h. So this is giving us the slope of our secant line. And then again, ultimately to get the slope of our tangent, we want to do the limit as h goes to 0. So this fraction that we see, a lot of times we call this the difference quotient, but it's really just the slope formula that we've seen before. All right, so what happens with this difference quotient? Well, the thing that happens when we go to try to calculate this limit is this difference quotient is always going to be a 0 over 0 form, which is going to cause an issue for us. So let's actually try an example where we go through and we calculate the derivative of a function using this definition. And we're going to do it for kind of an easy function to start with. So we're going to do it for the function x squared. All right, so let's start by writing down f prime of x, and let's write down this limit definition. So it's the limit h going to 0, f of x plus h minus f of x all over h. And the first thing we do here is we want to start working with this f of x plus h. This is usually the most complicated part of this process. So what we want to do, let's kind of do this off to the side, and then we'll fill it in. So you want to go to the original function, and you want to imagine, look at this formula, and wherever you see an x, change that to parentheses x plus h. So I see an x here, I'm going to change that to parentheses x plus h. I see an x here, I'm going to change that to parentheses x plus h. So I'm changing just that x. So the squared is still staying there. So essentially what we're doing here is we're just plugging in this fancy number. We're plugging it into this function. All right, so let's write that in. Let's fill that in. So we're going to have our x plus h squared, and then we write down the original function, which is just x squared. And that's just the original function there. So we have our f of x plus h right here, and then we have our original function next door with a minus sign in. So again, this is just the change in y, basically. All right, so then we're dividing this by h. So we have this limit to calculate, and our strategy is going to be multiply this out and then try to cancel off that h in the denominator that's ultimately giving us division by 0 here when we try to evaluate. So we're going to multiply out. So if we FOIL this out, we get x squared plus 2xh plus h squared. Then we have that minus x squared from before, and we're dividing this whole thing by h. So then from here, we can, usually all the stuff from the original function should get canceled off. And we see that we have an x squared and then an x squared, and we're subtracting in the middle. So those do cancel. So then our difference quotient simplifies to just 2xh plus h squared all over h. And again, we still have that 0 over 0 form. So we want to try to factor the numerator. And in this case, there is something that factors out. Both of these terms have an h in them. So we can factor out a copy of h. So if we get an h out, we have 2x plus h left over, all divided by h. And then we cancel. So the h's cancel. And if we look at what we have left, now this is just a regular polynomial. So the way we calculate a limit of a polynomial like this is we just do direct evaluation. And in this case, our direct evaluation, h is the thing that's changing. So we're going to do a direct evaluation at h equals 0. So when we do that, we get 2x plus 0. So we're plugging 0 in for the h. And if we simplify, that gives us just 2x. And this kind of matches up with what we would expect from power rule. So we know from power rule, we take the 2, bring it down, put it in front, and then we subtract 1 in the exponent. So we end up with 2x raised to the power 1. All right, so what we're going to see in class is we're going to practice this a little bit more. So we're going to try some more complicated functions where we have constants in front of the x squared, and then we're adding or subtracting constants, and then we'll see another example where there's more x terms. So we'll kind of see some different scenarios here, but the idea is going to be the same. We're going to want to multiply this x plus h squared out, and then eventually we want to get that h to cancel in the denominator. All right, so we'll see you then. Bye-bye.